What's up, everybody? Welcome to lecture 6. Yeah, I think it's lecture 6. Today we're going to be talking about section 1.7. And 1.7 is going to be all about this idea of the precise definition of a limit. And I'm not going to lie, this is one of the hairier parts of calculus, if not the hardest part. Just to initially get your head wrapped around this concept of what's actually happening inside of this definition. That said, the definition is as follows. If for every number epsilon greater than 0, there is a number delta greater than 0 such that, that's what this ST means, such that if the absolute value of the difference between x and a is greater than, or is less than delta and greater than 0, then the absolute value of the difference between f of x and L is less than epsilon. And we write that the limit is as follows. So we would say that if this definition holds, then the limit as x approaches a of f of x is equal to L, and it does exist. That said, what the hell did I just read? What does all of this mean? Well, let's take a minute to think about some of this. So, we're saying that x, the absolute value of x minus a is between 0 and delta. Well, what that really means then is that if you look between a minus delta and a plus delta, x is going to sit somewhere in between there, and so is a. So we're just pulling somewhere from this ball, that's the term that mathematicians will oftentimes use to describe this, from this ball, we're going to pull some x value. So this is, like I said, in math we call this a delta ball. And what we're saying is we have this symmetric group of values centered around a, right? So you take a, you add delta, you take a, you subtract delta. Any number in that collection, from a minus delta to a plus delta, you can choose an x in there. That x, you're going to put through your function, and it's going to give you something in the y-axis, right? So this represents what's happening in the x-axis. This represents what's happening in the y-axis. Now, over here in the y-axis, we've got what's called an epsilon ball. And what we're trying to do with this definition is show that we can pick any of these arbitrarily, any of these epsilons arbitrarily, and form this so-called epsilon ball around L. So any interval from L minus epsilon to L plus epsilon. And we can find a corresponding delta value such that if we pull an x out of this delta ball, we're always going to find a value inside of this epsilon ball centered on L. In other words, if I were to start closing this in, so making epsilon smaller, meaning fewer values around L can be our target, right? If I were to start shrinking that down, then I can always find a delta that when I center a ball around A and pick an x out of that ball, the function will always send values back to this. That is what it means for a limit to exist, and that is what this definition is saying. Is that if I were to shrink this thing down, I can always find another ball over here such that every x value inside of that ball will always map back over to this ball. So this is going to take some time to think about, to understand, and I want you all to take the moment to yourselves If it takes an hour, a day, it doesn't matter. But take some time to understand what this is actually saying. Because this is really what the limit's doing. It's saying that, hey, I can look at a smaller and smaller and smaller collection of numbers around L. And I can always find a collection of values around A in an appropriately small ball, such that the function will map back over to this. And the implications are that the limit exists, right? That's what we're saying here. That this is the proper definition of the limit. Having said that, let's look at how we're going to use this now. So as an example for how we're going to use this precise definition, let's consider this problem here. We know from direct substitution that the limit as x approaches 1 of x cubed minus 5x plus 6 is equal to 2. That's just because we can plug 1 directly in. That's what direct substitution told us. But if we wanted to use the precise definition of the limit, we could find a delta such that if x is within delta of 1, then x cubed minus 5x plus 6 is within 0.2 of 2. In other words, if we choose, in other words, what we're going to do is we're going to find a delta value such that if the distance between x and 1 is within that delta value, then the distance between our function and 2 is within 0.2. The way we're going to do that is by starting here, by considering just this. We're going to say, all right, we want this function rather, just this bit here. We want this within 0.2 of 2. Okay? And just to right here. Just rewrite it a little bit, right? But we could drop the absolute value signs if we wanted to, and rewrite this as the difference between our function and 2 is between negative 0.2 and 0.2. Well, what that tells us then is that we can add 2 to both sides to find that our function needs to be within negative 1.8 and 2.2. All right, so what do we do here? Like, where do we go from here? The next thing we need to do is we need to find the x values that satisfy those two conditions. We need to find the x values such that when you pass x through this, it comes out to be negative 1.8. And when you pass x through this, it comes out to be 2.2. That's what we need to do next. So I'm going to go ahead and let y'all work that out on your own. While y'all are working that out on your own, I'm going to go ahead and write up the rest of this problem on the board. So pause the video and we'll be right back. Alright, so by solving this inequality, by looking at what the upper bound of x is and what the lower bound of x is. So by saying, alright, what x value satisfies the condition that this equation is equal to negative 1.8, then what x value satisfies this equation when x cubed minus 5x plus 6 is equal to 2.2. When we solve that, we get these upper bounds and lower bounds. That x has to be between 0.92 and 1.12. But hey, we said that x has to be bounded between 1 minus delta and 1 plus delta. So we could just rewrite this in terms of deltas. But we need to be careful here. Because you notice that inequality is not symmetric around 1, is it? So we need to take a moment to say, all right, need some wiggle room here to identify the fact that there's going to be 2 different possible deltas to choose from. A delta on the left and a delta on the right. So 0.92 is equal to 1 minus delta L for the left lower bound, and 1 plus delta R for the right delta, or the upper bound, right? And that's going to be equal to 1.12. Well, if that's the case, we could just subtract 1 from all of that, couldn't we? Yeah, there's no problem with that. When we do that, we get that negative 0.08 is equal to negative delta L, which is less than x minus 1, which is less than delta R, which is equal to 0.12. In other words, delta L has to be equal to 0.08. And delta R has to be equal to 0.12. So the question now is, which delta is our answer? Take a minute to think about this. What we're trying to do is find the smallest delta that will guarantee, or I should say, we're trying to find the delta that will guarantee every x value inside of that delta ball will go inside of our epsilon ball. That's what we started with at the very beginning of this problem. That means we should probably go with a conservative answer here, right? The smallest delta ball ought to be the guaranteed answer. And that's what we're going to go with. We're going to choose delta L for our delta. And that's how we would solve this problem. We'd start by saying, what do we know about what's happening in our y-axis? Let's use that to figure out what needs to happen in our x-axis to guarantee what happens in our y-axis. So normally we work from x to y, right? But when doing these sorts of proofs, when working out these delta epsilon problems, you need to go from y to x. And we need to do some deeper thinking, some playing with and some real analysis here to understand what's going on. So starting from y, we were able to get that our function has to be bounded between negative 1.8 and 2.2. That tells us that our x value has to be bounded between 0.92 and 1.12. But that tells us that 1 minus delta L and 1 plus delta L has to be equal to those values accordingly. And then from there, we do the rest of the work. And that is really all I had for y'all on this section 1.7. There is more that the book covers and that the notes cover. I do encourage y'all to read those. But insofar as understanding the limit and understanding these, I think we're good for now. If y'all would like, I can certainly make another video just to go over the one-sided limits, the precise definition of the one-sided limits. But for now, I'm going to leave it here with section 1.7. Again, if y'all have any questions, shoot me an email.